Good morning, ladies and gentlemen. Let's talk about torque again. Torque is a twisting force.
And that's the Greek letter tau right there.
Tau for torque. Okay. A little bit of review. The axis of rotation.
This is the first of the three important ideas. It's a thing that, this was your shoulder when we were playing with the books.
Yeah, it's that thing that we're rotating around.
That's right.
And then we have the line of action, which is extended. We can draw that with a dotted line, and it's collinear with the force. So wherever the force is, it is.
That's when we had the plumb bob. The plumb bob was a force of gravity, and that goes down, but you could also extend the line up.
And then we have the lever arm, which is the distance between the line of action and the axis. And this is what's really important. It's on a line that is perpendicular to both.
Yeah, that's
So,
what that little...
Axis of rotation, this is the line of action, and it's perpendicular.
Yep.
Boom, right there. You can
Yep.
see it. Okay. Torque is force times lever arm.
That's such a simple equation. All you have to do is know what the players is. Gots to know the players before you can do the game.
Let's do this.
All
Do
right.
it. A little bit of review here. Well, which one is, what are my sides of the triangle here?
0.28 looks like the hypotenuse.
Hypotenuse, that's going to be my opposite. This is
SOHCAHTOA,
my
which
adjacent.
trigonometric function are you going to have?
So we're going to use sine.
Yes, ma'am.
Sine theta equals opposite over hypotenuse.
Yep.
And let's see, we're trying to figure out my opposite. Okay, so I'm just going to do the hypotenuse times the sine of theta. That's going to be my opposite. So that's going to be 0.28 meters times the sine of 50. And that is going to get me my answer. Okay, so 0.28 times the sine of 50, and I get 0.214. 0.28.
0.21.
0.21.
That makes sense. It's got to be shorter than 0.28.
Yeah. Just a little bit of review.
Just practice.
A little triangle review. Okay, which gear, y'all be riding bikes, which gear should you have the chain on if you are riding up a hill?
You know them gears that you can shift? You got the chain, you got the cogs. Here the chain is on the smallest gear, the tiniest gear.
And then here it's way out here, at the farthest gear out there.
You got them gears, use them, shift them. So if you're going uphill, which
Steep
one
hill.
should you have? So what's the physical principle that we're dealing here with, Ms. Moore?
Okay, well, the physical principle that we're dealing with here is torque. So for the same force from the chain, which gear will provide the greatest torque? Because no matter what, you're putting the same amount of force on there, right?
That chain pulls the same force that's due to how strong you is.
Yeah, so you're putting the same amount of force in there, so why do we have to change the chain when we're going up a hill? What's going on there?
We want greater twist. We
Greater
want greater
twist.
torque. We need to twist that wheel to make it go around to take us up the hill.
Well, let's take a look at this. So this is the small chain, and this is where the chain is on the big. This is where the chain is on the small, and this is the big ring.
Yep.
Big ring. And we know, y'all know how these work.
So
right?
there's only the same amount of force on each of them.
And this is coming from the pedal, right? When you
Yep,
do
yep.
the pedal, the thing goes around.
Pulling on the chain.
But what's different here?
Looks like one's got a longer lever arm, one has a shorter lever arm.
This is our lever arm right here. Bada boom.
What's
This
that
is the
equation
shorter
for
one.
torque again?
Well, torque equals force times the lever arm.
Oh!
So if we have
Guinness
the
must
same
watch
amount of
it.
force, but we have a bigger lever arm, same amount of force, but a smaller lever arm, which one's gonna be bigger?
Esto.
Yeah. So we want the chain that has the biggest gear on it. That is gonna be this one right here, and that's gonna give you the greatest torque, the greatest twisting force.
It'll get you up the hill easier. Now you paid for them gears on that bike. Use them, fool.
Okay. How does the equal arm balance find the mass of an object?
What's an equal arm balance?
7 miles. Okay. And you know what? I think we should go on this side, boy, so they can see the numbers and stuff. Okay, so this is an equal arm balance. And the question is, how can we figure out the mass of an object, in this case, my car? So
Oh.
right now, they're not equal, not at equilibrium.
It's not at equilibrium, but what's equal about this arm? What are equal about the arms?
The lever arms right here. So this is like the point of axis right here where it's twisting around,
That's
right?
the axis of rotation
Right there.
yeah.
And then this is a lever arm, and this is a lever arm.
And they're both equal length.
Yeah, and so, and so let's go ahead and just play around. So this is a 1 kilogram. Oop, too much.
That is too much mass.
Let's bring these over here a little more. Okay, this is 0.2 kilograms.
Not enough.
Oh, sorry, that's a 0.5. That's 0.2. That's too much. 0.5.
So 700 grams is too much.
500, 600.
There's 600.
650.
650. That's 20.
20.
670.
I'm glad you can count.
690. Go ahead and put that little bitty one on there. It's so cute anyway.
So cute.
So here we have 700.
Dope.
And that's too much.
Okay, so I'm gonna take this one off. So cute. What do we have right now, Boykin?
There's a little slider. We're at 690.
So what is it? What's happening when I'm moving this?
Okay, you're changing the lever arm for this guy.
Yeah.
Bigger, smaller, so that what you're doing is you're balancing the torques.
Okay, so I think we almost nailed it here.
Yeah, so the
So-
force on each side is the same.
And we got the force of gravity pushing down here,
Yeah.
and the force of gravity down here, and now they're at equilibrium.
And what those forces do is they cause a twisting force
Mm-hmm.
around that central axis. And the two torques, the torque on the left equals the torque on the right.
And one, they're counteracting. Counteracting.
I like that word.
Okay. All right. I think we talked about everything we needed to talk there. Okay.
Do you understand now how an equal arm balances finds the mass of an object? It's through torques.
Dork. Okay, so a rigid body can be visualized as a large number of points. So this is a rigid body, and you can imagine that it has a whole bunch of points that make this thing up.
Like those millimeters that are on there.
Yeah, and so there are two types of motion. This one. There are two types of motion for rigid body. We are going to be talking about translational and rotational. Now, in the past, we've been talking about translational, right? You just didn't know it?
Yeah. Well, translational means you go from one place to another. You translate from one place to another, like translating from one language to another. You over there, now you're over there. That's a translation in physics talk.
So a translational motion, all points move in parallel. So when I go from here to here, all these points are moving in parallel with each other, no matter what.
Yep, no matter what direction you move them, if it's in all points are parallel, translation.
Now rotational motion, so that would be something like this,
Oh,
moving like this. Rotational motion, all points move in circular paths with a common center point.
so the center point's where you're holding it, and every point on there is making a circle. Oh.
So we have to consider both of these types of motion as we move forward today.
Yes, ma'am.
Equilibrium occurs when all external forces and torque sum to 0. So before, when we talked about equilibrium, we were just focusing on forces summing to 0. Now we're going to introduce torques. That is, there are no translational or angular accelerations.
Yep, so all that stuff we were doing before about equilibrium, that was translational equilibrium. That's another word. You already know what it is. Now here's a word to describe it.
Yeah. And remember that the dynamic
Trinity.
the dynamic trinity? That's this idea here. If you've got no acceleration, our net forces are 0, equilibrium, and constant velocity.
That's right.
Same exact idea for translational and angular. Okay.
Sweet.
So torques can twist clockwise or counterclockwise.
Oh yeah, over here.
So let's see. So this torque, for example, is
Trying to make it go
clockwise, and at the same time, this one is going counterclockwise. I was about to say clockwise. I was like, that's right. That's the right way. And in doing so, they are canceling each other out, and they are in equilibrium.
Equilibrium. So that clockwise is called negative, I don't know why, and counterclockwise is positive. That's like if you get old, that clock going around is a negative thing.
Mr. Boykin knows about that.
I am.
Okay. If the 500-gram mass is at 65 centimeters, where should you hang the 20-gram mass to achieve equilibrium?
200 gram.
You should always start with diagram.
Remember we had the meter stick and we were hanging the things from them?
Same idea.
This is the same
Literally.
thing.
All right. So we'll call this middle part here 50 centimeters. And we said if there's a 500 gram at 65 centimeters.
Put it on the other side.
Oh, the side.
Remember that? Remember the
Oh,
mistake
yeah.
I made?
Oh yeah. Okay. Come on, it's more. Okay, right there. That's 60. That's 65. Okay. So right here, this is 65 centimeters.
Yeah.
Okay. And how much? 500.
That's
grams?
500 grams. Let's call that 5 newtons. Because that's half a kilogram. So that'd be 5 newtons.
And then it says where should we hang the 200 kilogram mass? So we know it's going to be somewhere over here, right?
Yeah.
So 200 grams, that's going to be 0.2 kilograms, which is 2 newtons.
2 newtons. So we got
Okay.
2 newtons of weight. And what we want to know is where on the meter stick should we hang this thing?
So the distance between here and here is going to be 15 centimeters, yes?
15 centimeters, yeah.
Okay, so we want to know what this is going to be.
Yeah.
And we know that at equilibrium, we want our torque 1 to equal torque 2, right?
Yep.
And we will call this our lever arm 1, and this will be our force 1, and this will be our force 2, and this will be our lever arm 2.
Okay. So what is torque?
Well, torque is force times our lever arm. And force 2 times our lever arm 2. And what are we trying to find here?
Well, we know both forces. We know one lever arm. We need to find.
Okay, we need to find that lever arm over there. Okay, so our lever arm 2 is going to be 5 newtons times, let's see, 15 centimeters. And our force 2 is going to be 2 newtons. Okay.
That looks like a ratio to me.
Yeah, so 5 to 2. What's 5 divided by 2?
2.5.
2.5, right? 2.5 times 15. We're going to get 37.5.
So L2 is 37.5.
Now, if you were like, Miss Moore, can I just plug it in my calculator? Do I have to do the whole ratio thing? Just plug it in. You know, you're gonna get the same answer.
Now they got to do the pyramid. You got to do the torque because the torque is the force is the lever arm. You got to do
Yes.
all that kind of stuff in order, because this is a simple one.
Yes, this is.
You have to build the skills with a simple one. So when it gets crazy,
It will get crazy.
you got the skill.
Not too crazy.
Okay, so we now know what L2 is. What's
So
the last thing?
This is 37.5 centimeters.
Where should you hang the mass?
Okay, well.
50 plus 37.5.
So over here is 0, right?
No, that's 100.
No, we're going this way, right?
Oh, you're right.
And then-
Yep, over there is 0.
So can I do 50 minus 37?
It's going to be 20 something, isn't it?
50 minus 37 minus that number. Oh, wrong. 50 minus the answer. And I get 12.5. Is that what you said?
Nope, I was wrong.
12.5 centimeters from 0, right? This is going to be right there. So,
What you've got is a meter stick with its pivoting at 50 centimeters. You hang the 500 gram mass at 45. You got to hang the 200 gram mass at 15 in order to get equilibrium.
wait, 15?
12.5.
Okay. I was like, wait, hold on.
Sorry.
Yeah, so right there, that's where you hang it. Okay. Good?
We got this.
Okay. Is the apparatus in both
So
translational?
when you do a problem like this, there are questions you have to ask.
Okay, so back to these words, translational and rotational. So my first thing is there any acceleration, up or down, or is it just existing?
No, it's in equilibrium.
It's existing. It's in equilibrium. So yes, it is in translational equilibrium. It's not falling. It's not rising up. It's just existing there. No
Right.
acceleration.
Correct.
Now tell me about rotationally. Is it rotating on any axis?
Not once you got the other mass in the right spot, the torques cancel each other out.
And it's at equilibrium.
Yes, ma'am.
So is the apparatus in both translational and rotational equilibrium? The answer is yes.
If it is, then
Make a diagram showing all torques and forces.
I think we've done that.
Okay, I think we have two. And let me just really emphasize here though. So if these are pushing down, or the force of gravity is down, which way is this one?
Well, that's right. There's a force, there has to be a force in the up direction.
In the up direction. Now this was at 50 centimeters. We'll leave that there. Okay, so do we have all of our forces and torques here now?
Well, we haven't put the torques in.
No, we haven't.
But, you know, I don't know, you've got, well, actually, we do. We've got the lever arms, we've got the forces.
Yeah,
So,
okay.
yeah, we do.
Okay, and do we want to talk about positive and negative yet? or
Well,
should we keep going? Let me see.
they are positive and negative. The clockwise, that 2 newtons.
Let's take a look.
is
Let's take a look
clockwise.
at our next one here.
All right.
This is gonna help us. Okay.
Go.
If the meter stick has a mass of 0.235 kilograms, so mass 0.235 kilograms, what is the vertical force exerted by the central pivot? Well, the vertical is going to be, the up, right?
He's got to eat, but the downs, we know what the downs are.
Okay, we know what the downs are. The downs are 5 newtons, 2 newtons, and we have to also factor in the
0.235 kilograms is 2.35 newtons, isn't it?
yeah. Okay, down. So then if we just add all of these 3 up, 5 newtons plus 2 newtons plus 2.35 newtons, right?
That's the total force down.
7, 8, 9, 9.35
Sure.
newtons. That's the total force down. Okay.
So we're in equilibrium.
We're in equilibrium. So if we want to know the vertical force exerted by the central pivot foot, that would just be the opposite of that, right?
Yes, ma'am.
Okay, so that's not the right color. So that's technically down. This is going to be 9.35 newtons up, or positive.
So draw that arrow right at 50 centimeters, and it's got to be longer than the other
Oh
two,
yeah, it's
right?
got to be basically all of them combined, right? Okay, so plus that thing, 9.35 newtons. And what we did here was all of the down, okay, was 9.35 newtons down.
Yep.
Okay, we just added this plus this plus this, and then we did the opposite, which was just the opposite.
And we've answered the question.
Oh, okay. A 530 Newton diver stands on a massless board. What forces are exerted on the board?
I think we need to look at the meter stick to understand what's going on.
Was I just gonna erase this? But
Nope,
with my
leave it
phone?
up there.
Okay, leave it up there.
We can erase parts of it.
Okay, so let's talk about the forces that are being exerted on the diving board or the meter stick here.
Yeah.
Now, so we've got some person at the end. We have this middle piece right here, and then we have this one right here. Which direction are my fingers pushing?
That looks like it's going up,
Okay.
and that one is definitely down.
Okay, so that means that if I was to let go of this, it would go down, right? Because I'm pushing down to keep it here. And this one, if I let go, it would go down, right?
Yes, ma'am.
So when we need to draw a sketch for this to start off. And when we draw our sketch, we need to put the direction of our forces. And so for this one over here, it'll be down.
Down,
This one up here will be
up.
up. And then over there will be, if I let go, it goes
You know what, Miss Moore?
down.
That reminds me of this.
What we just did,
Oh, yeah.
right? So
If we want to find this, there are 2 unknowns here. There has to be a procedure for finding the solution.
there is. So in order to find the torque for a 2-step problem, we've got 2 unknowns. We need to create a system of equations.
Okay, so this is called the torque 2-step.
2-step. I'm
With-
gonna erase all this, right, Boykin?
Leave the diagram up,
Okay,
but
yeah.
you can take the other stuff down.
I was trying to roll what we decided to and not to erase. So notice that I'm leaving my diagram up because we're progressing slowly here, and we're only changing a few things. Okay. So we're gonna have to create a system of equations, and so the first thing we have to ask ourselves 2 questions. You have to think about translational and rotational motion.
Let's do translational first. Let's put that arrow back in.
That back here, right?
Yeah,
Here.
that big tall one.
I want
The
to make it
big-
bigger. I keep on making it big enough. All right, so step one, translational motion. So my x-axis, my force that's going to be 0. My y-axis, my net force is going to be 0. What this is saying is we're at equilibrium here.
Yeah, and what
Okay.
is these directions are up and down. These forces are up and down. So we're looking at forces in the y direction.
Oh, you know what? Let me add these distances in here real quick. I didn't actually finish drawing my diagram entirely.
So
So
that's
over here.
1.2 meters,
Okay, and then over here.
3.4 meters,
Boom. And then what was
and
her?
this force is 530 newtons.
530 newtons. There we go. Sorry. Okay. All right. So back over here with our system of equations. So we were saying that we need to show that we need to represent this in equilibrium, right?
Yep, so we've got 3 forces, 2 down. Why don't you call that one on the left? Well,
Yeah. We'll call this force 1. We'll call this force 2. And this will be the force up will be force 3 or force up, right?
up.
Up. Okay.
So what kind of an equation can we make with this
Well,
for translational motion?
we just talked about how this has to equal that,
Yep.
right? Okay. So the
FUP equals,
is going to equal technically the absolute value, right? Because it's
Yeah.
going to be a positive number. These ones will be negative.
Yep.
And 530 newtons, right? Technically negative, but whatever. Absolute value.
Yeah, put a negative in front of it.
Negative, okay. And I could have said, F1 plus F2 right here.
You could have.
I'm just sticking that in there.
So now that's all the forces, the translational forces. There's only 3 of them.
Mm-hmm.
And you add the 2 downs, they equal the up, they cancel each other out. What's the next thing?
Well, the problem is here we have 2 unknowns like we just talked about. So we need to use our system of equations. We're going to get that from step 2, our rotational motion. Okay, so step 2, let's talk about rotational. This was translational. This is rotational. Okay, well, what do we know about? It says the torque net is 0. That means we're at equilibrium, right?
Yeah, we're choosing that fulcrum in the middle to be the
Oh, yes.
rotation point.
Yeah, and you could choose either one, right? Because if this is me, right, I could let go of this and it goes this way.
Yeah, so it rotates around
Okay.
this one.
Okay, or I could let go of that and it falls
It
this way.
rotates around that one. Let's keep it simple and use that one.
Yeah.
So you've got 2 torques.
2 torques. Yeah, so let's start with our pyramid. We don't want to get ahead of ourselves. All right, we've got 2
1
torques.
is equal to torque 2, and torque is force times the lever arm.
Okay. And which force are we missing? We've got force 2, lever 1, but no force 1. So I'm going to go ahead and solve this for force 1.
See how simple that is?
1. Okay. Should I plug it in here?
Yeah, why not?
Okay, so let's go 530 newtons times 3.4 meters divided by 1.2 meters. Okay. 530 times 3.4, right? And then we divide that by 1.2. And I get 1,500, we'll call it 1,502. Is that number?
Just call it 1,500.
1,500. I'm like, does that number make sense? And it does to me.
It's got to be bigger. Okay, so let's go to the next slide.
Oh. First period, okay. So solve a step for one variable and insert it into the other step to solve for the other variable.
I think what we just did.
Good morning, Cougars. Please stand for the pledge to our flag.
Go.
It's important every
Welcome back before we were so rudely interrupted by the bulletin. Okay, so now we've got the force 1, and I'm going to go ahead and take this.
Put that up there on our
Yeah,
diagram.
don't we need, oh yeah, you're right. Force 1 here.
No, that's a force up. Oh, no.
No, force 1, yeah, force 1.
No,
right?
force 1 is 1,500 newtons.
1,500 newtons. Okay, so now we've got this, and we've got this. Can't we just add these 2 together to get our up?
Yeah, that's this one right here.
Okay, it's going to equal 1,500 plus 50 newtons. So that's going to be 15 plus, isn't that going to be
11.
23? Is that,
Yeah,
wait, let's just,
2030.
that's what I'm thinking.
2030. How old will you be in 2030? That's 10 years from now.
Miss Moore will still be young. Always young.
Hopefully
Okay.
I'll still be breathing. But
It's kind of depressing. Okay. So our force up is going to be.
This is also your last chance to personalize your yearbook. Purchase yours today.
That many newtons.
now see how simple this is? The ups equal the downs.
Yeah.
They cancel each other out.
This-
But we had two unknowns. We only knew the 530 newtons. We didn't know the other ones.
Yeah. So we
But
call
the
it
torques also cancel each other out. And torque is just simple. It's force times the lever arm. We solved for the unknown, which was F1.
Google Classroom.
We found that it was 1500 newtons. And then we were able to plug that back into the other one.
Today, start with being thankful.
All right. So I think we're almost done. We're done
Stand
here.
by for practice.
Please show the Earth